In this video, we will complete our introduction to hypothesis testing by taking a look at the formal hypothesis testing process using P, or probability values. This will complete our introductory look at the two main inferential statistics techniques that we cover in this course. You may recall that we started by looking at confidence intervals, which are used when we wish to estimate the value of a population parameter, and today we conclude by looking at hypothesis tests, which are used when we wish to evaluate or test a proposed population parameter value. We've covered both inferential statistics techniques in the context of looking at population proportions, and in the future we'll do so looking at population means. Now, before we proceed with looking at how to perform a hypothesis test using p-values, you might recall that the last time we looked at how to perform a hypothesis test using a confidence interval. It turns out that technique is rarely used. So you might ask, why did we use that particular technique then? There are two reasons why we did so. First, I used that technique as a bridge to introduce the concepts associated with understanding how to construct null and alternative hypotheses. Secondly, I used that technique as a means of providing further practice in constructing confidence intervals. So without further ado, here's the scenario that I'm going to use as the basis for our discussion today. Suppose I state that candidate XYZ received less than 70% of the popular vote in the last presidential election. Note that 70% would be a population parameter, in this case, a population proportion. So our parameter of interest is the proportion of voters that voted for candidate XYZ in the last presidential election. The question here is this: how do we go about evaluating or testing the above statement? And the answer is we perform a hypothesis test. To perform our hypothesis test, we're going to use the same four-step process that we used when constructing confidence intervals. So we begin with prepare. As part of that, we can state two hypotheses associated with this scenario. The null hypothesis, the skeptical position, says that the population proportion of voters is exactly equal to 70% that voted for candidate XYZ. The alternative hypothesis is that the population proportion of voters differs from 70% that voted for candidate XYZ. And notice that that particular hypothesis is associated with the claim that we were making in the scenario. Next, let's go ahead and assume that we have a large random sample of 1,000 voters that we're going to gather data from. So moving on to our check step, since we now know that we collected a random sample of voters, we know that the independence condition is met. Secondly, we can quickly check the success-failure condition. However, we need to be careful because although we used the sample proportion when constructing confidence intervals, for hypothesis tests, we used the null hypothesis value, which in this case was 70%. So plugging that value in for p subscript 0 in the formulas for success and failures, we find that there are 700 successes and 300 failures, which represent numbers of voters, of course, in that sample. So in this case, because those values are both greater than or equal to 10, the success-failure condition is met. Lastly, for the check condition, for the check step, we can say that because both of the conditions are met, we can state that the sampling distribution of sample proportions is approximately normal. And we can then draw a normal distribution with the null value at its center, since the null value and the mean of the sampling distribution of sample proportions should coincide due to the central limit theorem. We now move on to the third step of our process, which is the calculate step. Before we draw a null distribution sketch, we're going to take a moment to calculate the standard error. And we have a formula, of course, for doing so. And notice again that in this formula for the standard error, we have replaced the sample proportion that we used when we were constructing a confidence interval with the null proportion value drawn from the null hypothesis. So that would again be the 7/10 value that is plugged in for the standard error formula. And so when we do so, we get a value of 14 thousandths for the standard error in this case. Now, Let's consider two possible sample proportion values for the scenario that we've been looking at. The first one is, suppose that I collected a random sample of 1,000 people and I asked them if they voted for candidate XYZ, and I find that 68% of them, that is 680, did vote for candidate XYZ. Would that data provide statistically significant evidence to reject the null hypothesis? Remember, the null hypothesis was that the proportion of voters was exactly equal to 70%. Is 68% far enough away from 70% to reject that null hypothesis? Okay, so that's one possibility. Here's a second possibility. Suppose I collect another random sample of 1,000 people, and this time 65%, that is 650 of them, voted for candidate XYZ. Would that data provide statistically significant evidence to reject the null hypothesis? In other words, do I think that 65% is far enough away from 70% to be able to say that the null hypothesis is going to be rejected? So at the right, I've provided two null distribution sketches, one for each of the proposed sample proportions. The top sketch shows a blue triangle at 68%, or 0.68. The bottom diagram shows a blue triangle at the sample proportion value of 65%. So which of the two sketches seem to show a sample proportion value far enough to the left, that is below, the null value of 70% or 7/10 to say that we would reject the null hypothesis? Well, to answer the question that I just asked, we need to define a criteria by which we can determine whether we reject or fail to reject the null hypothesis. We can't just simply rely on looking at the diagrams and thinking about whether the triangle is far enough to the left or not. We need something more definitive. It turns out that the criteria we will use is comparing the so-called probability, or p-value, with a quantity known as the level of significance, which we designate or denote with the Greek letter alpha. Take note of the following. The probability, or p-value, represents the probability of an observed sample proportion, or a sample proportion that is more extreme if the null hypothesis were true. Now, to find a probability, or p-value, we are going to find the tail areas in our null distribution corresponding to our sample proportion value. Take note of the following, that in this course, because we are always performing a two-tailed test, our probability, or p-values, will be a total of the left and right symmetric tail areas that are created on our null distribution sketches. Okay, so now that we've defined what a probability, or p-value, is, let's see how to calculate the probability, or p-values, for the two sample proportion values that we considered earlier. That is the sample proportion of 68%, or 68/100ths, and the sample proportion value of 65%, or 65/100ths. So let's start by looking at how to find the p, or probability value, for a sample proportion of 68%. Notice I've already drawn a null distribution sketch by scaling the p-hat axis in units of standard error, and that the null value of 70% is at the center. So we begin by finding the test statistic, z, capital Z, for the given sample proportion value. And I've shown the work on the slide there. I won't go through that. Notice the value is -1 and 43/100ths. The next step is to draw vertical lines through negative absolute value of the test statistic value and the absolute value of the test statistic value, and then label those values on the sketch using the absolute value notation to do so. Then the last thing we do is we find the area that is the probability, or p-value, that is in the tails bounded by the negative absolute value of z and the absolute value of z. We use RGuru to find that area. And I've noted the p-value in the upper right-hand corner of the screen. It's approximately 1,527/10,000ths. I would label the tail areas. Notice I've labeled them as being half of the p-value. And then we would shade those areas corresponding to the p-value over 2 on the left and on the right, the tail areas. And that's a complete null distribution sketch for that particular p-value. So now let's take a look at how to find the p-value for a sample proportion of 65%, constructing our null distribution sketch at the same time. So we begin by finding the test statistic z for the given sample proportion value. And again, I've shown the calculation work on the screen for that. We get a value of -3 and 57/100ths in this case for the test statistic value. So again, on the null distribution sketch, I draw vertical lines through negative absolute value of z and absolute value of z. I label those values on the sketch, and you can see I've gone ahead and done so using the absolute value notation again. And then the next thing that I do is I go to our guru and I find the area that is the p-value in the tails bounded by those vertical lines. I then go ahead and label the tail areas. Notice again, they're going to be labeled as being half of the p-value on the left, half the p-value on the right, so that the total area under the curve in the tails is the total p-value. And then I go ahead and I shade those. Notice in this case, the shading is very, very small because I have very, very small tails on the left and the right. So I've shown that with orange shading. So now that we've completed the calculate step for our two possible sample proportions, that is, we found the p or probability values for the sample proportions of 68% and 65%, and we drew corresponding null distribution sketches. We now come back to the question we asked before doing that. Namely, which of the two original null distribution sketches with the triangles seem to show a sample proportion value far enough to the left of, that is below, the null value of 70% or 7/10ths to say that we would reject the null hypothesis? Well, to answer that question, we will compare our p-values against the so-called significance level alpha. And here's the criteria that we're going to use. If the p-value is less than alpha, then we will reject the null hypothesis. Otherwise, we fail to reject the null hypothesis. So let's take a look at it for the scenario that we've been dealing with. For that scenario, we're going to let alpha, the level of significance, be 5% or 5/100ths. So the fourth and final step of our hypothesis test process, the conclude part, would be as follows. First of all, for the sample proportion of 68%, note that the p-value, that is 1,527 10,000ths, is greater than 5/100ths. Therefore, we would fail to reject the null hypothesis in that case. That means that the poll does not provide convincing evidence to support the claim that candidate XYZ received less than 70% of the popular vote in the last presidential election. Another way of saying that is that the 68% value was not far enough below 70% to reject the null hypothesis. Okay, what about when the sample proportion was 65%? Well, note that our p-value in that case was 4/10,000ths, which is much less than 5/100ths. In this case, we would reject the null hypothesis. And we would say that the poll does provide convincing evidence to support the claim that candidate XYZ received less than 70% of the popular vote in the last presidential election. And again, that's another way of saying that 65% was far enough below 70% to say that we rejected the null hypothesis. And that concludes this presentation.